let's say that you want to test whether tall people have more back problems than short people. So we would use something called the chi-square test. And the chi-square test is a test that is used to establish whether there is a link or not between two variables, two seemingly independent variables. So again, we're talking about tall people having back problems. So then we can establish what the two seemingly independent variables here are, which are height and back problems, or back health. In order to start our test, which is going to prove whether there is an association between our two variables, we need to establish a null hypothesis. You might have encountered this term before. A null hypothesis is basically the hypothesis that there is no link, that the variables are independent. There is no link between the variables. So height has nothing to do with back problems, and back problems has nothing to do with height. However, we have to establish our alternative variable, which is that there is a link. And so they are dependent to each other, these variables. They have a link. They're associated. So in order to start our chi-square test, the first thing that we need to do is to randomly sample a group of people. So let's say we have in a whole country, we will randomly sample 100 people. So we'll randomly get 100 people and get their height and whether they have back problems or not. And so with that information, we should make a table. So here is our table, and we have calculated how many tall people with back problems there were, how many short people with back problems, how many tall people with no back problems, and how many short people with no back problems. Now, these are our observed values, because we've observed them in our survey. But now we have to calculate what the expected values are. And these are the expected values according to the hypothesis, the null hypothesis, that there is no link, that they are independent, these two variables. So, in order to do that, we're going to need to calculate the totals. So, 19 plus 10, 29. So that's the total of people with back problems that we encounter. Then the total of people with no back problems would be 71, giving us a total of 100. Then the total of tall people would be 49, and the total of short people would be 51. Okay, so now that we have our totals, we're going to calculate our expected values. So let me erase this here. The expected values mean that these variables are not linked at all. So we can calculate. Let's start with the expected value for someone who is tall with back problems. So here, we can calculate the chance of someone, let's just say tall, and back problems. So let's calculate the chance of someone being tall. So you'd go to tall, and there are 49 out of 100 people who are tall. So the chance of being tall would be 49%. And multiply that, because it's and, we would multiply that by the amount of people who have back problems. So 29 out of 100 people. So it would be a 29% chance of them having back problems. And so we would get that the percentage of tall people with back problems, the expected percentage of tall people with back problems, is 0.1421. So out of 100 people, 14.21% are tall and have back problems. So 14.21 people, that looks like a 19, 14.21 people are tall and have back problems. Now we'll do the same with short people. So we want the expected value for someone who is short and has back problems. So again, we find the probability that someone's short, so 51%, and times it by the probability that someone has back problem. So again, 29%, 0.29. And that should give us 0.1479. So there is a 14.79% chance that someone who is short has back problems in our expected values. Remember that this is all our expected values. So, therefore, there are 14.79 people who are expected to be short with back problems. If we do the same thing for the rest of the values, of the expected values, we would get that the expected for tall people with no back problems would be 34.79, and the expected value for short people with no back problems would be 36.21. Seems easy enough. So now we need to calculate our actual chi-squared value. Right. Oh, it is important to note that in the chi-squared test, data can't be linear. So, and what do I mean by linear? I mean continuous. So you can't just have, for tall people, you can just have a set of values. You need to have categorical data. This means that the data that you collect has to fit in categories. So for example, for our survey, we have that people over a certain height will be tall, and people under a certain height will be short. So we just sort them into these categories, but we can't actually use the actual values of the height of those people. Anyways, so now, back to our chi-squared. We need to calculate the chi-squared value. The chi-squared value is equal to the sum of the observed minus the expected squared over the expected. So this thing right here means the sum. So in our set of data, in order to calculate the value, we would get chi-squared is equal to, let's start with the first data point. It's equal to, what is the observed? 19, minus the expected, which is 14.21, over, squared, over 14.21, which is the expected. And now we add, plus, what is the next data point? 10 minus 14.79 squared over 14.79, plus the other two data points, this one and that one. So therefore, our value, chi-squared value, should be equal to 4.46. I rounded up for simplicity's sake. But now that we have our chi-squared value, what does our chi-squared value really mean? What can we do with it? Well, in order to do something with this value, we need to calculate something known as the critical chi-squared value. And the critical chi-squared value is calculated using the following scary-looking table right here. But in order to use this table, we need to know two very important things. One of them is the probability level, otherwise known as the significance level. Significance level. And the degrees of freedom. That's what DF stands for. Degrees of freedom. Okay, so significance level in our chi-square test will be at 0.05 or 5%. What does it mean? Well, it means that there is a 5% risk that the test is wrong. So there is a 5% chance that if the test says that the null hypothesis is right, there is a 5% chance that the null hypothesis is wrong. Or if the test says that their null hypothesis is wrong and should be rejected, there is a 5% chance that it's actually right and it shouldn't be rejected. So we can deduce that the smaller our significance value is, the more accurate our test will be, because there will be a lesser chance that the test is wrong. So for example, if your significance value is 0.02, which is also 2%, there is only a 2% chance of the test being wrong. So it's less. However, the IB does usually use for biology 0.05 as the standard significance level value. So in our chi-square test here today, our significance level is 0.05. So we'll take a note of that. But now we have to talk about degrees of freedom. So the equation for degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So if we go back to our table, we have how many rows? We have 1 and 2 rows of data, and we don't count the totals. And then 1 and 2 rows, 1 and 2 columns. So some people wonder why in the degrees of freedom, why we do a minus 1. And this is because, if we look at our table, if we have this piece of data right here, 14.21, and we have the total, we can easily calculate what the next piece, what this piece of data should be. So therefore, we only really need one piece of data. And then in the other one, it's the same thing. If we know what this value is, and we have our total, we can easily calculate this value. Therefore, there is a minus 1, because the last data point, can always be deduced from the totals. Anyways, so let's go back here and calculate our degrees of freedom. The number of rows was 2 minus 1, and number of columns was 2, and now minus 1. So that gives you 1 times 1. Therefore, our degrees of freedom is equal to 1. Okay, now that's equal to 1. Now, if we follow this on the table, we arrive at this value. So our significance level was 0.05, and our degrees of freedom was 1. And now we have this value. And this value is what I said before was the critical chi-squared value. But how do we use it? Well, let me erase this part right here and show you. So, the rule says that if your actual chi-squared value is greater than the critical value, then your null hypothesis should be rejected. Hence, if the chi-squared value is less than the critical value, the null hypothesis should be accepted. Now, let's remind ourselves of what the null hypothesis was in our case. The null hypothesis is that there is no link. No link between the variables. So, if the chi-squared value is greater than the critical value, our no link hypothesis will be rejected. Therefore, there is a link between the values. They are associated. However, if the chi-squared value is less than the critical value, the hypothesis that there is no link is accepted. So there is no link between the variables. Now, in our case, we have a chi-squared value of 4.46 and a critical chi-squared value of 3.841. So we know that 4.46 is greater than 3.841. So our chi-squared value is greater than the critical value. Therefore, our null hypothesis should be rejected because there is a link between the variables. So there is a link between tall people and back problems. There's just a link between height and back problems. There's another way in which people can do this, check whether the null hypothesis should be rejected or accepted, and how accurate this is. There's another very clever way, which I will show you now. So let's forget about our previous critical value, and let's say we have let's forget about the chi-squared value. Let's say we have a new chi-squared value of 5. Okay, so what some people do is that instead of doing going to the table, seeing how many degrees of freedom you have, seeing what your established significance level is, and then looking at your critical value and comparing it to your chi-squared value, what they do is that they look at the chi-squared value, which is 5 here, and they look at the table, and they see within degrees of freedom 1, what is the closest value to 5, and that is this value right here. So then they assume that there is a 0.02, because then they look at the probability level or the significance level, and they assume that there is a 0.02 chance, so 2% chance that the hypothesis, that the test is wrong.